Okay, so hi everyone. As an introduction to the entire course, I think it's a good idea to go over some of the computational components that are available on the course Google Colab, which follows sort of directly the textbook itself. So I'll start off with an introduction and then move on in subsequent videos on portions relating to individual chapters. The introduction here is really an introduction to very basic features of Python on Google Colab. If you're familiar with them, you can feel free to skip it. On the other hand, the other portions that pertain on this document that pertain to the chapters, I would follow along as they tend to follow the algorithms presented across the chapter. So, in case you're unfamiliar with it, Google Colab is basically Python that you can run online. You have access to it if you have a Google account, such as a Gmail or something of that type. And right here, what I'm going to do is sort of introduce some really basic, as I mentioned, really basic things in part 1 before moving to chapter 1, useful class demonstrations, and subsequently, as I mentioned, further chapters. So let's start off with what we have here. So here I've just basically constructed a very simple while loop for people to sort of get a feeling for how while loops are constructed in Python. I would say in general that if you have any hard time at all understanding any given line of code, for example, it's super simple to copy paste into GPT to try to understand it. But generally speaking, we've tried to comment the code as well as we could. So in this simple while loop example, we start off with a counter that we set equal to 0. We subsequently start the loop, the while loop, which will stop at 10, and we iterate the counter by 1 at every iteration of the while loop, and finally print the value for the counter. So in this particular case, we would have printed the counter from 1 to 10. So if I want to run this code, what I do here is I press on this little arrow, very efficient, and it prints out sort of my 10 index values, my 10 counter values. One thing with Google Colab is that you can insert one of two things. One of them is code, the other one of which is text. So this here, example while loop, I've introduced text in order to be able to write this down. And this here is the code, which I compile at the top left. Here's another interesting one. It sort of is a for loop in the range of 1 to 10, and it prints out whether the number is even or odd. So in this particular case, it says that for I in the range of 1 to 10, if the remainder of I divisible by 2, if that's equal to 0, then we shouldn't print even. Otherwise, we should print odd. And so it alternates, of course, between odd, even, from 1 to 10. Next is something that we'll be using very often in class, and it's sort of how to define functions. In this particular case, we've defined a very simple function that adds and subtracts two numbers. So the function takes as its argument, here we can see it, num1 and num2. And right underneath, in this line here, we've defined what the function does with that input that we provide. It defines a new variable called sum, which is the sum of the two numbers, and computes a different variable called difference, which is the difference between both numbers. And the output of the function is the sum and the difference. So if we notice here, if we try to print out what is returned by the function, we remember that we have to give the function two arguments. That's number 1, number 2. And subsequently, the function constructs its sum and its difference, and it outputs 3 and minus 1, right? Here's something else that'll become very useful, and those are logarithms. And if we notice at the very top of this code here, this very first line, we have to import a library, and this library is the math library. Now what I'm going to do is I'm going to print out here the log base 10 of 100. Now in class, normally when we write log, the log is understood to be the natural log. But here in this particular case, we need to be very clear. And, for this example here, we've selected a base 10. In order to be able to call the log function from its library, notice that I do math.log. And then I integrate both arguments of the log. As another example here, I have print math.log5. And as I've written down in a comment here, is that if I don't specify the base of the logarithm, then at some level, just like we do in class, it assumes a natural log. So that's kind of really basic stuff for Python. While loops, for loops, defining functions, importing packages or libraries, and then, using them. Here's something else that's going to be very useful in class, and that's sort of how to draw samples of random variables. Now, in class, we'll be drawing samples from random variables of very complex distributions. But initially, let's start off with something very simple. In fact, something that the computer can do. And what we'll notice in class is that, a large part of our job will be to convert uniform random number samples into samples drawn from more complex distributions. But for now, let's start off with sort of calling out or using the uniform random number sampler in Python. So the first thing we do is that we import the package, again, numpy, or numerical Python, and we'd like to refer to it as np. So here what I'm doing is that I'm importing numpy, and I'm going to refer to it as np. So when I call a function or something within it, I can use np dot and so forth. So what I'm going to do is I'm going to generate 10,000 samples. Those will be the number of numerical samples drawn from the uniform distribution. And finally, I will generate an array of these random samples using np.random.uniform. And this is the uniform distribution. Notice how it takes 3 arguments. So in this particular case, I want to draw uniform samples from the uniform distribution between 0 and 1. In principle, I could draw numbers from the uniform distribution between 0 and 100, right? It doesn't need to be between 0 and 1. So I specify a lower bound, that's 0. I specify 1, my upper bound. And finally, I also specify the number of samples, which I said was 10,000. So this random sample basically outputs an array of 10,000 numbers drawn uniformly between 0 and 1. I've commented out, and if you notice here, there's a pound symbol. I've commented out the print symbol because maybe it's not so interesting to look at the output of 10,000 numbers generated between 0 and 1. But if we want, we can sort of comment this out and maybe look at just 10 of them, which shouldn't be too bad. I will run this, and now it'll print out those 10 numbers in the array. And we see that all these numbers here are between 0 and 1. So let's go ahead and bring it back to where it was. And keep going. So once I have random numbers drawn from a distribution, what can I do with them? So one thing that's often done, as a form of post-processing is histogramming the data. So in this particular case here, I've imported a different package. In this case, the package is matplotlib.pyplot, and I will refer to it as plt. So now, if I'd like to plot a histogram of the uniform random numbers that I've just generated, I will do this, plt.hist, that is the histogramming function, and I will histogram my 10,000 samples. Oh, and I should probably rerun this to make sure that, right, the array is now 10,000 in size. I've generated 10 bins, so I've selected to generate 10 bins in my histogram. Alpha here just basically specifies the transparency of the color bars, not super critical. I want my histogram to be blue, and I want the edges of my histogram to be black. These are just choices for now. And of course, I can add X labels, Y labels, and give my histogram a title. So if I do this and I compile, remember that I've generated 10,000 different numbers this time, so the histogram may not look exactly like this, but let's go ahead and plot it, and it looks a little different. One thing that we notice immediately is that the values are between 0 and 1, and that they're roughly all equal, which is what I would expect if my samples were uniform. Now, what happens if I generate far fewer samples, let's say 1,000 here, and then I try to plot my distribution, my histogram here? It's fewer samples, so actually there's going to be a lot more spikiness that I anticipate in my histogram, exactly as I see here, right? And maybe I can make my number of bins larger, and the information is going to be even spikier, noisier, exactly as so. So at this point, let's make the number of bins, well, we can keep it at 100, increase the number of samples, maybe to 10,000, run this, rerun that. I'm pressing Shift Return here, and I'm back sort of to where I was. Maybe I want kind of broader histograms to make it look nice. And there it is. It's kind of flat. Now, maybe something else that I'd like to do is not necessarily to bin or to histogram my samples, but rather to actually look at what the samples look like as a function of the sample number. So remember, I've generated, in this particular case, 10,000 samples. So here I'm going to be plotting, whoops, it's a bit too dense. Let's make it 1,000 samples, just to make it clear. I'm going to rehistogram this to look at what that histogram looks like. And then let's plot this here. So a couple fewer samples. So what am I noticing here? I have 1,000 sample numbers, and these numbers seem to be scattered between 0 and 1. Well, that makes sense. Maybe this point here appears like it's at the furthest left. So that was my first sample. Maybe this one here was my second sample. This one here was my third. By the time I get to here, maybe that was my, well, it's somewhere close to my 800th sample. And if you notice, the samples are just uniformly scattered between 0 and 1. And that's kind of what we see here. We can also do this for 10 samples just to make it very sort of less dense and a little bit clearer. Histogram will look very noisy because I have very few samples. And here you go. My first sample was at about 0.8. My second sample was at about 0.38, let's say, and so on and so forth. So my samples are sort of scattered between 0 and 1. So let's move back to 1,000 where we were. Generate that histogram here, Shift Enter on my computer. Generate what these samples may look like, and then move on. Another thing we can also do is not just to draw samples from uniform distributions, but some languages such as Python actually allow you to draw samples from a number of sort of well-established distributions, and in particular the case of the normal or the Gaussian distribution. So if I want to draw samples from a normal or a Gaussian, again, I import numerical Python. I'm going to import my plotting library. My samples here will be 10,000. I have to specify the parameters of the Gaussian. If you haven't seen the video the videos for chapter 1 yet, you'll be introduced to these shortly. But if not, let me just say that a Gaussian is a distribution with two parameters. The first parameter is the mean, and the second parameter is the standard deviation, which squared is the variance of the distribution. So the mean basically tells you where the distribution is centered, and the variance tells you how broad the distribution is around that mean value. Finally, what I'm going to do is I'm going to plot an array of numbers, or I'm going to generate, I should say, an array of random numbers, all generated from the normal distribution, with the mean and the standard deviation specified. And as a third argument, I have to specify the number of samples, which I've selected to be 10,000. And finally, what I'm going to do is I'm going to plot my histogram, my samples. Again, I selected 100 bins, alpha is equal to 0.7. I specified X label, Y label, and plot title. If there's other things that you'd like to do to this code to modify, do fancy things, I don't know, maybe you want a grid in the background, or maybe you want vertical lines, at various points here on your figure, I would simply go to GPT and say, how do I modify this code in order to introduce the following? I should also say that there is an AI prompt in Google Colab when you open a code box. So it should be, you can also in principle do it directly here. This is another example. I don't think it's super important, especially not for this class. But in principle, you could also fit your Gaussian to a curve, to the best fit curve. I'm going to leave this here because, again, we're not going to be doing a lot of fitting in this class. But if you were to choose to fit, then this is kind of a very simple code that you would use here. Finally, as I mentioned, you don't just need to sample from a uniform or Gaussian. You may have to sample from an exponential distribution. And in this particular case, since we'll be doing this very often, maybe it's worth talking about it for just a little bit. So briefly, I think I've repeated this a couple times. We first import the numerical Python package and refer to it as NP. We'll generate 10,000 samples. If you've seen chapter 1, you know that the exponential distribution has one parameter. Otherwise, you can take my word for it. For now, I have to specify that parameter, and I choose to call it scale. Sometimes we'll notice in class that scale parameter takes on a different name. For physical applications, oftentimes we refer to this parameter of the exponential distribution as the rate. But either way, I'm going to generate an array of these random numbers drawn from an exponential. I specified the scale for that exponential. I also specify as my argument the number of samples, which in this case is 10,000, and the rest is something that's very similar to what we've seen before. And I can go ahead and generate a histogram. So let's go ahead and recompile this. We notice what this histogram looks like here. If I recompile it, it's going to generate 10,000 new random numbers. So the histogram may not look exactly like this, but it's going to look pretty similar. So let's go ahead and compile and see what that looks like, right? Looks a little different, it looks a little different from what it did before. Finally, this is something we'll be doing pretty often, and that's manipulating vectors and matrices. So very briefly, again, I've imported my package. I've defined a matrix, in this particular case is an array. This is a 2x3 matrix. Here I've done something a little bit different. I've generated a 2x3 matrix, but populated by zeros. And I do that by specifying NP, so within the NP library, dot zeros that generates an array 2x3 populated by zeros. And then I can choose to assign new values to those zeros. So for example, I can choose the 1, 1 element of my matrix 2 to be equal to 7. And I can choose the 0, 2 element of matrix 2 to be minus 2.5. So I can populate values of that matrix later. In other words, what I'm doing here is I sort of allocated memory to this object matrix 2, and then I've started assigning numerical values, individual numerical values to the elements. And finally, I've printed matrix 1, and I've printed matrix 2 here. So we can go ahead, recompile it again. It'll generate exactly the same things. Not a big deal. I can change this to an 8 and just make sure that it works, and it does. An important thing. The 1, 1 element here, since Python starts counting from 0, would be the second element that we notice here. So an array, it starts counting from 0, and that's an important point. Adding and subtracting matrices. So for example, in this particular case, I can take the sum of the matrix or the difference of the matrix and output the two results. But I think probably more interesting is sort of matrix multiplication. If you literally take two matrices and multiply them, then Python will do an element-wise multiplication. That may or may not be what you're looking for. You may be looking for genuine matrix multiplication. So for those matrices whose dimensionality allows for multiplication, you would use np.matmul, matrix multiplication, use have as its arguments two different matrices, and then output the matrix product. In this particular case, we've generated a new matrix, which we're calling matrix 3. So with that said, this completes sort of the basic introduction to programming with Python before we move on to class demonstrations for Chapter 1. Thanks, everyone.